Here, we also provide an intuitive geometric understanding of the training process of a perceptron. If we consider the model parameters with a little bit more details, for now, let's forget about the bias as we have always emphasized that it can be considered a weight of a special associated with a special data feature. So forget about the bias now. Then let's consider how the model parameters, the weights, contributes to the computation of the h values. Sometimes I use another symbol to represent the value in this slice. Sometimes it's called a values. It's a little bit confusing, but the relationship is clear. If we consider the contribution of the model width to those values, we'll see that the weight has exactly two elements to be multiplied by the two elements of each data point. So with this setup, the weights have the exactly same format of the data points. We might as well consider a weight as a virtual data point in the data space. Then let us draw a link from the origin of the data space to every single point in the space, which makes every point a vector. So those values, I call them A because I want to emphasize the fact these A values, or the value returned by the H functions, are the alignment between the virtual data point, the vector of the virtual data point, with the real data points in the data space. Here is the X vector, and there is the W vector. And the inner product measures how the X vector aligns with the W vector. So with this understanding, the design of the learning algorithm becomes very intuitive. If, for example, the class label at data point is positive, and the prediction, unfortunately, at this point is negative. So the right thing to do is try to improve the alignment of the model weights with this data point so that the alignment will be mirrored as a positive one, or at least to be increased towards the right direction. On the other hand, if at some data point the right direction to change the alignment is negative, we would like to have the W negatively aligned with the X as possible. So to update the W to achieve this goal, if you want the alignment to go to the positive direction, it's easy. We just increase W with the X. If you want the alignment to change to the negative direction, we then update the W towards the negative X. So here is a set of examples. Or well, one example. These are the examples of the training steps of a perceptron. This is a simplified classification problem from the iris flower. I take two classes rather than three. I think Satosa and Versicolor. I call one class to be -1, the other to be +1, -1, +1. And I built a perceptron to separate the two classes. remind ourselves that the perception works on the data space rather than single data points, while including the single data points. So this perception split the entire data space into two parts. For one part, it's called negative class. For the other, it calls it predicts as positive class. It's not difficult to see for this perception. It predicts the training samples correctly for those set and this set, but it makes mistakes on a few data samples. According to the perception training algorithm, we then randomly select one sample from those wrongly classified sets. For example, this one. Okay, and then we update the weights using the x value of the sample. Now let's bring back our bias. So the bias is associated with a special attribute that is to be constantly 1. So when we update our perception parameters, we update the W using the X values, and we update the bias using either positive 1 or negative 1, depending on the Y value, the target value of this wrongly classified sample. So after the update, the perception now behaves like this. So obviously, it has changed its behavior at this point, so much so that it is now classified correctly. But that is only with respect to one data sample. And unfortunately, we are now making a lot of errors on this set of sample. So don't worry, excuse me. We then select one sample from this wrongly classified group and repeat the procedure. Now, I think it's not completely the clearest thing, but you can see it has chosen this sample for its next step, updating of its weights. So after the next update, it improves its behavior on not only this one sample. Actually, it hasn't achieved the correct classification on this particular sample, but it does improve its behavior. It has improved its behavior on this set of samples. So we repeat this procedure for many steps, and finally, we arrive with a correct classification. Believe it or not, with a very simple proof method, we are guaranteed. Although the training algorithm focuses a step at each training iteration on only individual samples, but if if there ever exists one set of optimal model parameters that classifies the training samples all correctly, then the perception training algorithm will find one set of parameters that behaves completely correctly on the training samples. We will see this proof, a sketch of the proof shortly.